Welcome to the GOTO podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Hello, my name is Anne Currie, and I will be giving you your quick 10-minute introduction to my new book today. This is the third podcast in the series on the book Building Green Software, which has just been published pre-published, early release published on the O'Reilly website. So my name is Anne Currie. I have been in the tech industry for nearly 30 years now, which is quite germane to the topic we'll be talking about today. And I'm part of the leadership team of the Green Software Foundation, which is a Linux foundation for being greener in tech and managing the energy transition. But here today, I'm here to talk about the book that I'm currently in the process of writing along with my two co-authors, Sara Bergman of Microsoft, who you will have heard in the last podcast, and Sarah Sue, SRE at Goldman Sachs, who you will hopefully hear in one of our future podcasts. But today I'm here to talk about the latest section that we've released, which is chapter 2 of the book, code efficiency. Now, the question that we need to be asking ourselves today and in the talk today is code efficiency the key to being green and to have efficient and energy transition aware software? And the trouble is, it's quite a controversial question and a very controversial answer, I'll put it to you. Everybody's been really looking forward to the code efficiency chapter, and I know why, because we kind of think code efficiency is absolutely fundamental to cutting down the amount of energy and electricity used by software as it runs. And so I got into the green software about 7 or 8 years ago now, and it was entirely based on code efficiency. So my background, and obviously I've been in the tech industry for a long time now, since the early 90s. And back then, code had to be really efficient because machines were about 1,000 times less effective than they are today, about 1,000 times less good in terms of CPU, storage, speed of bandwidth availability, and cost. But 30 years, exponential growth really pays off. 30 years of Moore's law improvements in hardware and computing hardware have meant that we are about 1,000 times better now than we were then. And remember, these are all changes that happened within one career. It's not the end of my career. I'm not intending on retiring tomorrow. During my career, without completely spanning my career, we've seen 1,000-fold increase in the ultimate thing we all run on, which is hardware. So my interest in green software came from the fact that 30 years ago, we had to be a lot more efficient in the way that we coded because we had so much lower amounts of resources to run on. And we used to do a lot of things that I was extremely familiar with because I used to do them myself to get that increased efficiency. We used to use very low level languages. So I was a C developer, C server-side developer in those days. So you're looking at languages that are compiled, that run directly on without any kind of intermediation. On the hardware. And what that means is that you've got a lot fewer CPU steps per operation that's made. And yeah, you can run stuff today on a machine nowadays. It's unbelievable. We had nothing like this. And also their bandwidth as well. We had nothing like the bandwidth that's available now. And my original thought on being green was, okay, we can do all of those things again. We can go back to using, let's say, modern equivalents of highly productive languages, which Rust is more popular these days, and rightly so. It's a lot safer than C or C++. But it is an equivalent language that's not compiled and that is running directly on the hardware. And it's extremely efficient, as well as being a lot safer than C was. But fundamentally, it's the same concept. You've got a fast, very lightweight language running, and you use it to write clever code that kind of accommodates its own multi-threading. So one of the things that's very important is effective multi-tenancy if you want to write very efficient code. And back in those days, we used to do it by writing but actually we didn't, even back then, we didn't really write monoliths. We wrote something that would be analogous these days to microservices, not as tiny as modern microservices are, like meatier microservices. So you had a fair amount of you had a distributed system, but it wasn't quite as small as microservices. But it wasn't as monolithic as a monolith. And the reason why is because you wanted to try to emulate multi-tenancy. So something that happens these days in data centers, if you're in the cloud, something like that, you will be using VMs or even containers to get multi-tenancy. So you've got multiple different clients running multiple different systems on top of the same hardware. And the reason why that is good is that you'll have some things that are currently quiet and other things that are busy. And you can, by sharing the same hardware and being careful about how you balance up, so what's running on that hardware, you can aim to get really, really good machine utilization. And back in those days, machine utilization was absolutely key. We had such rubbish machines. We needed to make sure that they weren't ever sitting around waiting on operating system calls, for example. We had kind of feigned multi-tenancy that came with multi-thread. And it was great. It worked really, really well. I mean, it really was 1,000 times better than what we get these days. And my original thought was, if we had 1,000 times more efficiency in data centers these days, then the software industry would be a leader in the energy transition. We wouldn't be moving the dial when it came to using electricity. These days, we're about the same as most other industries. In data centers, we use about 2 to 3% of the electricity used on the planet across all sectors. But if you factor in hardware and end user devices, we're more like 12 or 10 to 12% according to Greenpeace. But if we just look at data centers, then if we could drop that 1,000-fold, then we're out. We don't need to worry about it anymore. We're completely done. So my original thoughts, the reason why I got into green was from my background in code efficiency. But we're not in the world that we were in 30 years ago. We are in a very, very different world. And I went in, all guns blazing on green software, although I didn't call it green software. I didn't call it green software back then. I called it sustainable software or coding for the energy transition, which is not what I'm allowed to call the book because, frankly, it's not very catchy, is it? But it's all the same idea. How do we code in a green, sustainable way that's energy efficient, energy transition aware? And I was thinking, great, what we'll do is we'll write everything in C. And then I started to do some work with customers, some work with businesses, some work with engineers about what people actually wanted to do and what was likely to land as a message. And the trouble is that rewriting everything in C or rewriting everything in a multi-threaded kind of somewhere between a microservice and a monolithic way, it's really hard. It's really, really hard. Back in the 90s, it used to take us ages to do anything. And it was very hard to change software. It's really hard to evolve software. And most of the 1,000-fold increase in machine productivity between then and now went not into making everything run faster on smaller and smaller machines. You know full well that isn't what we did with it. What we did with it instead is we improved developer productivity. So we put in loads of layers, isolation layers that made it easier as a developer, but not just made our lives easier. It made it faster. It made it safer. It made it more secure if you're using it all correctly. And that wasn't crazy, because actually the world has become different in the past 30 years. Expectations are very high that we move faster. We do iterate. We do get product features out in minutes, not years, as it used to be in the early 90s. And nobody wants to go back to that world. So if you start selling code efficiency to your business or more generally, you're going to run into that straight away. That nobody quite rightly wants to go back to that world. A lot of those things didn't really scale in the way that we need these days. It couldn't be made secure in the way that we need these days, and it couldn't react and get better and evolve these in those days in the way that it can now. So we need code efficiency, but we also need to keep all of those improvements that we got in the past 30 years. If we don't get both, we're never going to sell code efficiency. You're never going to sell code efficiency to your business if it's like, oh yeah, but we'll massively slow down our development cycles, because you go out of business. So we've got to find a way of squaring that and getting both of them at once. And I'm very sad because I really went into this in the hope that I could just tell everybody to rewrite everything in C and we'd be done. And a lot of people want to hear that. There's loads of us out there who would really love to rewrite all our code in C. But for the more sane amongst us, because we don't want to go back to that world, much as I enjoyed it in the time I was much younger. That's not the world that we can go back to. We need to be secure. We need to be fast. So we need to find a way of both but code efficiency is still really important. So how do we do both? How do we get that 1,000-fold increase in productivity, in machine productivity, without taking a 1,000-fold decrease in developer productivity? We have to align those two. And the more I've been looking into it, the more that my co-authors and I have been looking into it, the more we've been thinking we need to align it with open source, the cloud, and modern services. It really, when it comes to code efficiency, we need to make this a buy or a select choice rather than a build choice. Because if we can buy or select, push our suppliers to create efficient software, we can just buy it and they can keep improving it under their feet. Because although it's massively bad for developer productivity, that doesn't matter so much if you're selling code that's going to thousands and thousands of users. It's worth putting in that investment to get efficient code. So as a customer, which we all more or less are, I'm thinking that most of the folk who are listening in on this call on this podcast today will be consumers more than producers. When producers, I'm talking about people who have thousands or hopefully millions of users, but multi-million end users fundamentally of the underlying software that we need to make efficient. And if that is the case, then it's really well worth your while putting in the time and energy to make that code efficient. And it does require enormous amounts of time and energy. And as a consumer, which we are here at this point, if we can be putting pressure on our suppliers to put that work in, then we get so much more bang for our buck. So for example, here's an example. Most of us, it's not worth rewriting your code in Rust or Go, because even doing that is a hell of a lot of work. And these days, often quite unnecessary. The Python compiler. Now, there are now compilers for Python available that will compile your Python down to C, or even machine code. So there are people at the platform level who are working on making it so you don't have to rewrite your code in C or Rust in order to make it efficient. You can keep using these high-level, relatively easy-to-use languages where you get great developer productivity, but still get the code efficiency improvements. But what you need to be doing is picking those platforms that are moving in that direction and where you can just rely on and lean on the platform to develop the code efficiency for you. So, for example, say you're somebody who does choose to write Go code, which is really quite an efficient language. It's not quite as good as C, or Rust, but it's really quite an efficient language. Even if you choose that, you're better off putting pressure on the engineers behind Go, the community behind Go, to make sure that it is efficient. So, for example, you can write as efficient Go as you like, but if the standard libraries in Go are inefficient, then you've wasted your time. You're much better off putting pressure on the Go Go community to make sure that the standard libraries are efficient, so that what you write on top inherits that efficiency. That is a much more, that's an action that moves the dial when it comes to being green. Just writing your code in Go without putting pressure on the platform, the environment that you're working in, to be green under your feet and to continue to make it green under your feet, is a much less effective action. It's the whole thing about, if you want to go vegan, that's totally fine, but it's not going to change the world unless you are some kind of massive influencer who's going to make 1 million people go vegan. Then great, fill your boots, go vegan. There's no problem with that. But if you just do it on your own, it makes you feel better. That it doesn't change the world. It isn't going to get us where we need to be. What we need to be looking at is actions that are going to affect thousands of people. And in the software industry, the actions that are going to affect thousands of people are where we persuade our suppliers to be greener, not where we are greener ourselves, unless we are a supplier, in which case, yeah, definitely go green. But if you're not a large scale supplier of software industry code, where you need to be putting your pressure on is on your suppliers. And it's easy. It's easy, so much easier than rewriting your code in C, I can assure you. Is that get on the phone to your AWS supplier or whoever you're getting your platforms from and say, I really care about this. What are you doing? How are you doing? This is how I'm going to be making my platform decisions in the future. Yes, I want to see action. I want to see commitment. That's how you move things. That's how you change things. And I really wish it wasn't the case. I really wish I could be saying, gotta rewrite all your code. Because I love that kind of thing. And that is, it gives me a flashback to my youth. But unfortunately, that is not really the way that we're going to change things. We really, really need to be putting pressure on as consumers, as users of software, rather than rebuilding all our code. So the chapter, I really enjoyed the chapter. I really enjoyed writing this chapter of building green software. Although for me, it was heartbreaking. I enjoyed writing it. It forced me to rethink all my inbuilt desire to go back to those days of multi-threading and but really, really, really difficult to write languages that were close to the operating system. I used to debug assembler back in those days. Just don't do it. It takes ages. And you will get fired. So we need to find you a way of working that is both more effective, good for your business, and less likely to get you fired. Which is, don't rewrite all your code in C. Slows everything, even Rust slows everything down massively, unless you are actually writing open source software that you expect to be used on a massive scale. Even if you do, interestingly, two of the examples that came out when I was researching this chapter were from somebody who had tons of money, was expecting massive scale, and still didn't do the optimization until really late on in the day. And I think this really tells you quite a lot. So one example is you'll have heard earlier this year, there was a lot of fuss over it coming out that Amazon Prime Video used to run on serverless, but has been now moved to something which is more like, quite like the description that I was just giving about you. It's not full microservices. It's not a monolith. It's somewhere a little bit in between. It's like we used to do when you were writing your own code that was kind of essentially provided your own multi-tenancy by using multi-threading and a moderate degree of microservice and distributed systems. And they did that, and they said, "Oh, well, this is great. Now that we know that Amazon Prime Video is massively successful and needs incredible scale, we're willing to put this investment in to do this." And everybody went, "Oh, serverless is terrible," because it's, they've had to move away from serverless to get massive multi-tenancy and massive scale. And yeah, you will probably, but still, they had huge amounts of money to throw at it, and they still didn't start on that. They started using serverless, which is a pretty decent way of getting multi-tenancy without having to put in enormous amounts of personal engineering effort into doing it. Amazon, with something that they were absolutely betting on and had been betting on for years, didn't start by being super efficient. They started by concentrating on developer productivity, which is serverless, and then saying, well, that was good enough to get to up to this stage, and then we'll do the actual investment, which was similar to what we used to do in the 90s, to get to the next stage, but not until this year, which is amazing, isn't it? The other example is Teams. Microsoft Teams during the pandemic. They moved over to, they absolutely needed to they needed more machines, but they couldn't get their hands on more machines. So they decided, oh, well, how can we free up some of the wasted resource in our existing system? So they started to do quite a lot of the stuff that we used to do during the 90s. So rather than having, for example, storing all their data in text, text, we'd never have used text in the 90s, in data in their databases, they moved over to binary encoding. And that was what we used to do. We used to do everything was binary code. It was awful. It was impossible to debug everything. We all got quite used to being able to just read binary encoded messages. But anyway, thank goodness those days are gone. But anyways, Microsoft now, those days are back. They have gone back to using binary encoding to store data, so that they need much, much less hardware to store the data that they're saving. And they had to. They were forced to do it because Teams were going bananas, and they just didn't have the hardware to do it. It was like being back in the 90s, and apparently it was terrible. It was a really unpleasant experience, but they did achieve it. It can be done, but even Microsoft and Google and Amazon, on products that they had been betting on for years and had enormous scale, they didn't do this investment until quite late on. And I think that's it breaks my heart. But fundamentally, it is the lesson we need to be taking away from this. How do we do green? How do we do code efficiency without having to do those things ourselves? And the answer is we need to buy it. We need to put the pressure on our suppliers to give it to us. Whether those suppliers are Amazon, it's very easy to put pressure on Amazon. Just talk to your Amazon rep. Same with Azure, actually. Talk to your Azure rep. Open source communities, start raising issues. Start saying, well, how do I measure this? Is this good enough? Are these libraries good enough? Are these standard libraries good enough? That's the first thing to be testing. And really, it's a good measurement. Our last chapter was on measurements, but one of the easiest ways to just do some quick measurement on whether a standard library is good enough is just straight up performance. Is it fast enough? Is it fast or is it slow? If it's slow, raise a bug about it, because we absolutely need these things to be, these underlying technologies, these platforms to be code efficient. And that is where, unfortunately, we need to be putting our pressure, our our attention and applying our pressure. Now, if you want actual things that you can do, the build part of buy and build, that will be not in the next chapter that's coming out, but in the chapter after that, operational efficiency. Because when it comes to operational efficiency, there's tons of stuff that you need to do yourself to improve efficiency. But code efficiency, really, unless you are a platform, you need to be putting pressure on platforms. So I know, I feel sad. I would really have liked it if I'd just been able to tell you about how to, tune your for loops better. But really, the answer is don't tune your for loops better. Just put pressure on your suppliers to improve your compilers so that your code will be automatically tuned under your feet, and then just you write your code in a way that is compliant, is how your platform expects, and what your compiler will be optimizing based on, what will be optimizing optimally, if you know what I mean. So I'm sure that I will be back and speaking to you again about the operational efficiency in a couple of months' time.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.